My name is Forrest Glines. I am a graduate student at Michigan State University working with Philip Greda and Brian O'Shea, and this is our work looking at intermittently driven magnetized turbulence simulations. Diffuse astrophysical plasmas like the CGM and ICM are almost universally turbulent. Fast flow velocities at large scales and weak viscosity at small scales make them ideal conditions for turbulent flows, such as in this interstellar cloud shown here. Since the turbulent flows of these plasmas are chaotic, they're impossible to predict exactly. However, we can understand the turbulence from a statistical level from macro to microscopic scales. One of the primary tools for understanding turbulence is the energy spectra of the fluid. In a turbulent flow, energy is injected into the fluid at large scales, beginning as large eddies. These large eddies break down into smaller eddies via fluid instabilities. This is a transfer of kinetic energy from large scales to small scales with less energy contained at smaller scales, which is otherwise known as the turbulent cascade. Eventually, the eddies become small enough to dissipate on scales where viscosity is important, and the kinetic energy dissipates into thermal heating. In galaxies and galaxy clusters, this happens on the order of the cyclotron radius, typically tens of kilometers, much smaller than the dynamical scales of the galaxy. Since there are so many orders of magnitude between the production scale and the dissipation scale, current feasible simulations of galaxies and galaxy clusters will under-resolve the full turbulent spectrum. However, we can still describe the slope of the energy cascade between the production and the dissipation scale. In a hydrodynamical flow, the kinetic energy scales as k to the minus 5/3. However, introducing magnetic fields makes everything much more complicated. In a magnetized plasma, we no longer have just a kinetic energy reservoir, but there is also a magnetic energy reservoir with its own spectra. Kinetic energy can transfer back and forth between the magnetic energy and between different length scales. The magnetic fields affect the mechanics as well of the turbulence cascade. Just like in hydro, though, we have a downscale turbulence cascade, except both within the kinetic and the magnetic energy transferred via advection and compression. But there are also transfers up the cascade, an inverse energy transfer. There can also be transfers far down the cascade, a non-local energy transfer, where large-scale energy transfers into very small energy. As a result of these additional interactions, magnetized turbulence does not behave as nicely as hydrodynamics and is not completely 100% well understood. For example, what does the power law of the spectra look like? Is there a universal power law at all for magnetized turbulence? Last, for the case of this study, just to make things even more complicated, we're not just looking at stationary turbulence where there is a continuous driving force, but instead we're looking at intermittently driven turbulence, where large-scale, infrequent events drive the turbulence. For example, a supernova can introduce a one-time kick of energy to the plasma, which decays later into turbulence. Other examples of intermittently driven turbulence include galaxy and galaxy cluster mergers. Here we're more interested in how the turbulence develops over time. One system used to study intermittently driven plasmas is the magnetized Taylor-Green vortex. This is a chaotic, turbulent flow that decays into turbulence without the need of an external driving force. We explored a suite of simulations of the vortex with different subsonic Mach numbers and initial magnetic energies, and we performed a thorough analysis of this turbulence, which you can find more details of in our paper, Magnetized Decaying Turbulence in the Weakly Compressible Taylor-Green Vortex. Just as a highlight of our analysis, we found that the spectral index of the turbulence, the slope of the turbulent cascade, evolves as the flow decays over several dynamical times, and it differs depending on the initial field strength. So looking across 3 different simulations with decreasing initial magnetic field from left to right, quite often we found that the spectral index is flatter than the 5/3 scaling in a hydrodynamical turbulent cascade, approaching or even going below 4/3. Or in other words, there's comparatively more energy at smaller scales and more turbulent dissipation in a magnetized plasma. And when the kinetic energy greatly exceeds the magnetic energy in the rightmost simulation, it takes a few dynamical times before the kinetic energy spectra matches the magnetic energy spectra. Note that the magnetic energy spectra develops before the kinetic energy spectra. To investigate this further, we performed an energy transfer analysis. This is where we take the Fourier transform of different terms by which the plasma can exchange energy between the kinetic and magnetic energy and between different length scales. This energy transfer can be by compression, advection, or tension in the magnetic fields. We use this analysis tool to track how energy is transferred locally within the fluid, both downscale and upscale, and non-locally throughout the fluid. For example, these are plots of the shell-to-shell energy transfer as generated by the energy transfer analysis. These particular plots illustrate the familiar turbulent cascade, albeit through a different lens. These are plots of the energy transfer within the kinetic energy on the left, within the magnetic energy on the right, as facilitated via compression and advection, at early times in the top row and at late times in the bottom row. Orange here denotes a positive flux of energy from wave number Q to wave number K, and purple denotes a negative energy flux. The orange immediately above the diagonal and the purple below the diagonal show a downscale energy transfer between local scales, between very similar length scales. This is exactly the mechanism that drives the turbulent cascade as is seen in hydrodynamical flows. This cascade takes a few dynamical times to develop. You can see at early times the transfer at small scales is quite small, and at late times it is fully developed. Interestingly, in the high initial magnetic field simulations, the cascade is temporarily reversed. This is where energy moves from small scales to large scales for a short period of time. So this purple above the diagonal and orange below indicate local upscale energy transfer within the magnetic and within the kinetic energy reservoirs. This happens only at large scales in the kinetic energy, but happens at all scales of the magnetic energy spectrum. This particular transient inverse energy cascade is not observed in continuously driven turbulence simulations, only in these intermittently driven turbulence simulations. In the small initial magnetic field simulations, we saw significant non-local downscale energy transfer at early times, as shown by this orange patch far above the diagonal. This is an energy flux from the initial large-scale kinetic energy to all scales of the magnetic energy, as facilitated by tension in the magnetic fields. This non-local energy transfer is what leads to the fast development of the magnetic energy spectrum when the initial magnetic field is weak. Finally, just to summarize, turbulence is everywhere in astrophysics, and we understand it statistically rather by exact predictions. However, magnetic fields and intermittently driving forces complicate the theory. In our magnetized Taylor-Green vortices of intermittently driven turbulence, we observe no universal spectral index between different initial magnetic fields, and in fact we saw that the spectral index evolves over time. However, it can be shallower than the hydrodynamical turbulence, with comparatively more turbulent dissipation at small scales. Last, we showed an energy transfer analysis to explain some pieces of the energy spectra of the different reservoirs. Again, you can check out our paper if you want to know more about the energy transfer analysis. In the future, we'll be applying this turbulence analysis to some high-resolution galaxy and galaxy cluster simulations that we're just now assembling. So, thank you for listening to my talk.